We tend to think of teaching mathematics as a straight line. A teacher holds a pure mathematical truth and hands it directly to a student. But raw scientific knowledge is far too dense for immediate absorption. It requires didactic transposition, a deliberate mutation of a complex concept into a teachable format. This diagram illustrates the classroom's ecosystem, the didactic triangle. Learning is generated by the continuous tension between teacher, student, and knowledge. The line connecting the teacher and student represents the didactic contract, the unspoken web of expectations dictating how the class functions. If a teacher always solves the hardest part of an equation, the student learns to wait for rescue rather than struggle through the logic. Building genuine mathematical understanding requires the educator to layer multiple cognitive frameworks. The teacher must select the specific epistemological theory that matches the complexity of the current mathematical task. Navigating these relationships turns a teacher into a didactic engineer. Success in this environment depends on precisely calibrating the interactions between the learner and the subject matter. Behaviorism offers a highly efficient tool for drilling specific processes, like the steps to solve the equation 3x plus 2 equals 14. It relies on a cycle of stimulus and response, using repetition to cement a procedure into memory. This approach creates biological calculators. Students can execute memorized algorithms perfectly, but they often fail when introduced to a novel problem that requires abstract reasoning. Crossing the threshold into abstraction requires David Ausubel's principle of meaningful learning. For long-term comprehension, a new concept must actively anchor itself to a cognitive structure the student already understands. Consider percentages. Teaching them as an isolated formula of fractions and decimals yields poor retention. However, anchoring the math to calculating commercial discounts, a concept the student already navigates in the real world, gives the abstract numbers immediate utility. While behavioral repetition builds necessary neurological pathways, cognitive theory provides those pathways with semantic meaning. Jean Piaget established that true knowledge is built through cognitive conflict, a moment of deliberate intellectual disruption. Imagine a student whose internal logic dictates that multiplication always increases value. Then they are asked to multiply 8 by 0.5. The answer is 4. This paradox shatters their fundamental rule. To recover, the mind moves from assimilation, trying to force-fit the data into old rules, to accommodation, where it modifies its logic to reach a new state of cognitive equilibrium. Lev Vygotski's socio-constructivism shows that this equilibrium is reached faster through social scaffolding. When students work in groups, their differing problem-solving strategies collide, accelerating the accommodation process. Mathematical errors are the essential friction required to upgrade the student's cognitive operating system. Max Wertheim and the Gestalt theorists argued that learning requires perceiving the total structure of a problem, rather than just the individual parts. You can memorize the definition of a perpendicular bisector as a line cutting a segment at 90 degrees, but Gestalt theory emphasizes insight, the moment the student visually perceives that every point on that bisector is equidistant from the segment's ends. Jerome Bruner leveraged this idea through discovery learning. The educator designs a progression where the student uses inductive reasoning to discover mathematical rules for themselves. To teach why the angles of a triangle sum to 180 degrees, Bruner's method starts in the physical realm. Students cut the corners off a paper triangle and arrange them on a straight line. Only after they see the flat edge do they move to the symbolic algebra. Mathematical mastery is a structural awakening. It occurs when a student finally sees the hidden architecture connecting isolated numbers. Since mathematical cognition is dynamic and layered, relying on a static, uniform, standardized test is a significant failure. Dr. Okacha-Dur's methodology maps intelligence as a matrix of distinct, evolving capacities. This granular approach tracks specific cognitive growth rather than relying on a generalized IQ score. This infographic shows formulas used to quantify capabilities across 3 indicators: MIL for logical mathematical, MIA for artistic, and MIP for expressive personal. The MIL calculation isolates analytical problem solving, tracking competencies by dividing responses by a strict baseline of 30 to measure abstract reasoning capacity. Measuring artistic and expressive indicators tells a math teacher how a student visualizes geometry and how effectively they utilize the zone of proximal development during group work. Evaluation now functions as a dynamic, quantifiable diagnostic tool. It provides a real-time record of cognitive growth, moving past the limitations of traditional scoring. Looking at this scale, we see how qualitative behaviors, like the confidence to solve a problem versus the need for continuous scaffolding, are coded into a standardized quantitative tracking system. This practical test targets adolescents, using numerical pattern completion and geometric mapping to measure their exact capacity for abstraction without relying on language. In this high cognitive load evaluation, educators introduce intense visual noise into diagrams to track the threshold where a student's pattern recognition begins to break down. All of this data feeds into the Intelligence Discovery Notebook. This longitudinal tool shifts to focus toward tracing cognitive evolution over a span of years. Modern didactics is a precise engineering discipline. It requires fusing a deep understanding of psychological mechanisms with rigorous, multi-dimensional tracking to build the mathematical minds of the future.